So today we will talk about expanded decomposition, and let me recall the concept from last time, right? We talked about the notion of cut expansion, which we said that a node weighting A is expanding in G. This is the sound from me. Okay. The node weighting A is expanding in the graph G if what is the case? Can anyone recall?
Yeah. The capacity of the edges crossing the cut is greater than or equal phi times the minimum of A and V, A of S and V, or A of V minus S.
Yeah, exactly. Thanks. What's your name?
Akbar.
Akmal.
Akbar.
Akbar. Thanks. Yeah. So yeah, we basically want to say that for every cut, the cut size S to V minus S. This cut size is kind of big compared to the A mass on this side and A mass on this side. Right? It's not too small compared to like to both of the side. Like yeah, this is like at least this side or at least this side. Okay. What is this sound? Okay. And the cut that doesn't satisfy this one, we call it phi sparse cut. Okay. So A is expanding in G if there is no sparse cut with respect to A in G. Okay. And that's the example of 1 over 2 sparse, because there are like 3, the mass of A is 3 here, more than 3 here, but this is just 1. The capacity here is 1. So this is just from last time.
For this example, could we also say that A is, I guess, 1/3 phi expanded?
Yeah, like it's barely 1/3 basically, because we need it to be strictly smaller than 1/3. So like 1/3 plus epsilon sparse. Yeah. And the graph is we said that the whole graph, not just the node weighting A, the whole graph is a phi expander if the degree node weighting is phi expanding. So it's kind of like the whole node weighting is phi expanding.
Are we going to be working with many different A, or is it mostly just going to be degree?
You like most of the time we think of A as degree, but it's gonna be just the case maybe in this class. Like you think of A as the degree node weighting, but like next class already we will think of different A. Yeah. So okay. So first thing is that like I want to just mention quickly that expander are great. The reason is that whatever problem you want to solve on expanders, usually it's just become, like what problem you want to solve, it's just become easy on expander. And throughout the course you will see many examples, but let me just start with one. Okay? Yeah. Expander are just algorithmically friendly. And the first example is the problem of minimum cut, ST min cut. Okay. So, okay. So in this problem, what you have is a problem where you have a graph. Input is just a graph, and the vertex set S and T, right? And you want to find, let's say that the output is a cut S, right? Such that S is in S, but T is not in S. So this is just like a ST cut. This is what we call ST cut. If it contains S and it doesn't contain T. Okay? So this is ST cut. Okay? And what we want is that the goal is that the capacity of this ST card is minimized. And sometimes I just gonna denote this thing, this capacity that is minimum ST cut by lambda ST. This is just a value of ST min cut. Okay, so now one can solve this using Max law. How to solve Max law? I put the link in the course announcement that you can look it up how to do it. Okay, it's not trivial how to compute this thing. People know how to do it in polynomial time, like n cube time some times ago. Just a few years ago, now we know how to do it in how to solve this in almost linear time. Okay. Now on expander, I said that I can approximate this value in constant time. Okay. You don't even need to do anything much, just like constant time you can do this. Okay. And the reason is this. The reason is that this value, lambda st, is just sandwiched between two values that are just so easy to compute. So it's just suppose that you know the degree of every node already. So you just say that I claim that this value lambda is at most mean of degree of s and degree of t, and it's sandwiched by this part too, which is basically the same thing but with factor 5. Okay, is the claim clear? Yeah.
Does the right side of the inequality come from, like, because just s on itself and t on itself are also st cuts? Or?
Exactly. We're gonna explain this, but that's exactly why. The reason that lambda st is at most mean like degree of s and also at most degree of t. It's just because if you look at a graph and you have s and you have t, well, a singleton cut is a candidate of an ST cut. The singleton cut is a candidate of an ST cut. So min cut is at most this cut and at most this cut for sure. So this direction is kind of clear. Okay. But it's going to be the case that lambda st is at most this too. Okay. So why is that? Okay. So it's going to be almost from the definition of expander, and I want you to try to do this now. Try to prove this. I give you like 2 minutes. Okay, so should I proceed? Okay, you Akbar.
Yep. Would it come from the fact that we know that G is a phi expander, so like for any cut S, the degree function would be phi expanding, so it's kind of like from the definition, I guess, or?
Almost, yeah, basically from the definition. So let's see. Let's just look at any ST cut S, right? And now you know that, well, S is in S. And T is not in this part. So you know that, okay, from the definition, this capacity is at least phi min of degree S and degree V minus S. But this thing contains S, so it's at least degree of S. This thing contains T, so this is at least degree of T. That's it. Yeah. Okay. Questions about this? Okay. So you see, okay, if phi is close to 1, then you can get good approximation of any min cut value, any pair of ST min cut value, like immediately. Then you don't need to do it much, just look at the degree. All right. So, but you know, now I want to talk about expanded decomposition. Reason is this. Reason is that not all graphs are expanders. You see example like a dumbbell graph is not an expander. So like you cannot hope to just get like to solve approximate min cut easily all the time. But the point of expanded decomposition is that you can make G to become a phi expander just by removing phi fraction of edges. So no matter what the graph is, you can kind of modify phi fraction of edges of a graph so that the graph becomes a phi expander. Okay. So let me be more formal. So think of this as like some graph that is not an expander. Maybe this part is a clique or something. And the theorem says this. So given any graph and parameter phi, then there exists a set of cut edge, see? Such that first, this cut has size something like phi times m. Throughout the whole course, usually I will not like be so careful about log n factor. Although I will write it down when I talk about it, I just kind of don't really talk about it. I just kind of skip it. Okay. So C is going to be of size something like phi times m. Like so phi fraction of edges. And here I think of the graph as unit capacity, right? Unit capacity. And moreover, once you remove C from the graph, then the degree not varying becomes phi expanding in this G minus C. Okay. So let's try to pass this by looking at the picture. Okay. I start with some graph G that is not an expander. I have parameter phi. Then, by the way, if degree of G is phi expanding in G minus C, it means that G minus C is a phi expander. Why? Because if degree of G minus C is phi expanding in G minus C, then G minus C is a phi expander. But here I even have something like stronger, right? Degree of G minus C, degree of G is more than degree of G minus C pointwise. because G minus C is a subgraph of G. So this node weighting that is more than G minus C is even expanding in G minus C. So G minus C is a phi expander. Okay, let's look at the picture just so that you understand this more. You start with a graph which is not a phi expander. Then I just kind of remove small fraction of edges. Okay. Then let's look at each component after I remove this cut. Then each of the component is phi expanding. And G minus C, so it means that G minus C is phi expander. Right? Because to say that G minus C is a phi expander, it just means that each component is phi expander. So you don't need to understand why this is the case yet, like why C exists yet. I just hope that you understand the statement right now. Okay. And the size of C here, size of C is like something like phi n. So you think of C as like the thing that kind of decompose the graph so that each component become an expander. That's why we call it expander decomposition. You remove things and each component become expander. Right? Question about the statement?
Why would each component be a phi expander on itself, by itself? Yes.
Why would this become a phi expander?
Yeah, just
We will this need a proof, like why we have this actually. Yeah, I show the proof soon.
Will this be useful because like don't we remove the connectivity of the graph as a whole after we
Why
remove
would
some
this be
edges?
useful?
Yeah.
Because we do remove something. So it's not so clear how to use it yet, but at least you get some intuition that you remove small fraction of edges and everything else become good. So now you just need to focus on this small fraction of edges.
Okay.
That's the intuition.
In the size of C, phi log n plus moment by 2m or is just the phi n?
It's this thing. I just said like I don't care about constant. I usually don't care about log n too. So that's why I just write approximate phi m. This is how you think intuitively about this statement. Yeah. But this is a formal statement.
Just want to ask, what is M over here then, sorry? What is M?
M is the number of edges.
Okay.
Yeah. Throughout the course, m is the number of edges,
Okay.
n is number of nodes.
Oh.
All right. Okay. And before I show you the proof, let's even look at the more generalization of this, which is an expanded decomposition for node weighting A. Okay. So this is going to be true, like this kind of generalized to any node weighting. So you are now given G and A and phi. And I'm just gonna say that like the size of C, you can remove, like you can find a cut of size something like phi A. Recall that A here is just as, sum of A over all nodes. And then A become phi expanding in G minus C. Okay. So the previous slide is just when A is a degree node weighting. Okay, so what do we have? You have that suppose that A is not really phi expanding in G, then you might just remove this part and then look at the connected components in the, like after removing C, then each part become expanding. In each part, A is expanding inside. So here there can be sparse cut here, but it's not sparse cut with respect to A. So this A is expanding in this part. Okay. So you remove C so that A is expanding in G minus C. So again, C kind of decompose the graph so that A become expanding in each connected component. Now we're gonna prove why this exists. Right? Cool. Okay. So the algorithm is gonna be almost as straightforward as it can be. So you just say that you have some graph, you have A. Now initialize your cut C to be empty. Okay. And you ask yourself, is A is expanding in G minus C? So in the beginning, you just basically ask if A is already expanding in the graph. And if it is, then you don't need to do anything, right? Just return C as empty set. That's it. But it might be the case that A is not expanding in G minus C. So if it's not expanding, there must exist a phi sparse cut. If it's not phi expanding, just by definition, there exists a phi sparse cut. So in some component, right now the whole component is just like this whole component is just the whole graph. So just phi sparse cut like this. Okay. So this cut will be such that the capacity, or right now I just think of unit capacity. So the number of edges is less than the A on both sides. Right? And find that cut, then cut it, like include the cut edges to C. And then you now check again if, now after removing this cut from the graph, you check if A is expanding in G minus C. It might not be still expanding, so find another cut. So this is like maybe a component U. So now there exists a sparse cut as U minus S such that this thing, this cut here, is small compared to A from both sides. So cut it. And you look at, and so you add this to your cut and proceed. You might cut it again, and now it can be the case that you cannot find any more sparse cut. So once you cannot find it, then you return to C. So it means that once you are done, after terminating, A just must be phi expanding in G minus C, just by definition how you define the algorithm. That is, in each component here, A intersect component U, A intersect U here, is expanding inside GU. Okay. So this we have for sure. So what remains is what? We just need to bound the size of C. Question up to this point.
Do we care about like how efficiently we can refine these sparse?
We will care in maybe like next 2 weeks or 3.
Okay.
Yeah, like all this we can at the end we can do it with some approximation in nonlinear time.
Okay.
But yeah, right now, like checking whether there is a sparse cut exactly like this is actually NP hard. So okay, more questions? Good. All right, so let's try to bound the size of C. Okay, and our plan is going to be like some kind of amortized analysis. So we will start by saying that for every node that has some node weighting A, okay, I'm just gonna give money this much to that node. So for every node vertex B, I give them this much money. And then whenever I put some new edge into my cut C, I'm gonna pay $1 somehow using this money. Like some guy will pay for it. Okay? And I guarantee that without debt, like just by using this initial money, I can pay $1 to each edge in C. Just by using this initial money. If this is the case, then it means what? It means that C in total need to be at most this much, right? Because I have in total, the total initial money is just this much, and I just use this one to pay for C, 1 per edge. So the number of edges in C is this much. Make sense? Okay. So let's try to analyze this. Okay. So just imagine that like at some point I find some new sparse cut. This is like some new sparse cut, and I add it to my C. Whenever I add this thing, I need to pay. Okay. I need to find some way to pay for it. So what I'm going to do is that maybe do I have picture? Good, I have picture. So let's say that this is the component U, and then there is like a sparse cut here. These are the new guy in C that I need to pay for. Okay, and I said that I just let A vertices on the smaller side of a component to pay for this guy. So in this case, maybe like let's say we have S and U minus S, okay? And let's say that suppose that the number of nodes on S is smaller than the number of nodes on U minus S. So S here is on the smaller side of the cut. I will use the money of A vertices on the smaller side to pay for this guy. Okay. How much this guy on the smaller side will pay? This much. Like everyone has this much money, this thing times log n. From the beginning, I will use this much to pay. So what do we have? If each of this node pays this much money, then the total budget that we get from the total money that we get from vertices in A is like it's at least 5 times mean of this thing. So S, like because what we get here is like we get money of this much, 5 times AS, but 5 times AS is at least 5 times mean of the thing from both sides for sure. Okay. So we have this much money that someone paid for us, but the cost that we need to pay for C, the cost is just the number of edges crossing the cut. Okay. Now I just claim that like the cost that we need to pay is just at most the budget that we have. Why is that? Well, because S is 5 sparse. So it means that the number of edges, this is the cost. It's just at most the budget. So we have enough money to pay for the cost. Okay. Question up to this point?
Would it be strictly less or
It
less
will
than or
be strictly less. Yeah. Understand it. Strictly less. Okay. Yeah.
What the sentence each A vertex being the smaller side pays theta multiplies AUV. What does this mean?
It means that every node in A here, for example, this node V, let's say this node V. This node V will pay, like give us some money. How much? Like this many dollars. And every node here will give us this much money. So in total, we get this much money.
Is the A here the function we define, or is some graph of G? Like that?
A is some node weighting. It's just a node weighting. It's a fixed node weighting in the beginning. More questions? So what do we have so far? We have that when I introduce some new cut, I show that like some people, I will use the money that I have from the beginning here. I kind of decide how things pay off. Like I will use the money from the nodes here to pay for the new cut edges. Okay. But I need to show you that and the money that I get here is enough to pay for the cost here, because this is a 5 sparse cut. But I need to show that okay, so from the perspective of each node, it has some initial money, and sometimes it need to pay off, pay the money to the cut. I need to say that at any point of time, every node still has at least 0 money, so there's no debt. Okay. So why is that the case? It has this much money from the beginning, and at some point, whenever some node is on the small cut, on the small side of the sparse cut, then it pays this much. Okay. Why is it the case that at all time every node will have at least $0? Yeah.
It's like each of the cut is almost half the size of the previous one. So there's plot in it.
Exactly. So this is asking how many times one node can be on the smaller side of a cut. When it is on the smaller side of the cut, then the size of the component shrink by half. So the number of nodes shrink by half. But it starts with n, it shrinks to n over 2, then it shrinks to n over 4. How many times this can happen? Log n times. Right? So every vertex can be on the smaller side of a sparse cut log n times. So that's why if you pay this much per time, then this initial money is enough for every node. Okay. So that completes the proof. I just now show you how to pay, just put some money in the graph from the beginning, and then how to just use this much money, how to use this money from the beginning to pay for every edge in C. Questions? All right. Yeah.
Is the capacity 1 for each edge? Is that what?
Right now capacity is 1. Yeah. And I encourage you to think of how to generalize this for capacitor graph. Yeah. So basically, how much you need to pay will be basically the capacity of that edge. Instead of 1. So in capacitor graph, so what we prove is just this, right? And in the capacitor graph, you basically will have that the capacity of C is going to be at most 5 log n times the size of A. Yeah. Just that. Instead of the number of edges in C. This is in incapacitated graph. And I will from now call C here like the phi expanded decomposition of phi ED of A in G. That's what we're gonna like. This is like a key object that we will work with a lot from now on. So yeah, internalize this. Okay, and when A is the degree node weighting, it just like translate to this one. This become degree of G, and the size of degree G is just 2m. Okay. And I call C here like just phi expanded decomposition of G. Okay. All right. So now I'm gonna proceed. Question before yeah.
Does this end up being unique?
No, it's not unique. Yeah. Like just by the proof, you can see that there can be many sparse cuts you could choose. Yeah. All right. Okay. So next is a new it's an object that I call it repeated expanded decomposition, and the idea is that now we're gonna try to build and at the end of the class you'll see how useful expanded decomposition is. It's gonna how to make it useful is through this thing. Okay. So what is repeated expanded decomposition? Well, the idea is that you have a graph, then just compute expanded decomposition C of the graph, and then try to recurse on the graph induced by these cut edges. Okay, so let me tell you more precisely. Okay, so I put the box of just so that you can recall what is expanded decomposition. Okay, so now let me tell you what is repeated expanded decomposition, how to construct this thing. So I'm gonna repeat something like log m times, and what we're gonna do is just actually I should say that set G1 to be G, like G1 is the original graph, and then I just loop log n times. Then I compute Ci plus 1 to be something like 1 over log expanded decomposition for G, for Gi. Yeah.
Where n is the number of...
N is the number of nodes.
Oh, because we don't reduce that.
Yeah. Okay. Okay. So I compute this thing. It gives you some set of edges, right? And then I just say that I let Gi plus 1 be the graph induced by these cut edges. What do I mean by induced by the cut edges? It's just a graph such that all edge set of this graph is just a cut here. And then repeat, go to the next I and repeat. So let me ask you first, what's the size of C2? Can you give me some? Yeah.
Would it be less than or equal m over 2?
Very good. It's just less than m over 2, just from here. And then what's the size of C3? Another way to see this is C2 is less than half of the size of G, the number of edges in G1, right? And C3, well, it's going to be less than half of the size of edges in G2. But how big is G2? Well, G2 is just the same as G2. So this is at most this much. So you can see that it just gets half and get half and half and half. Right? So that's why we know for sure that you don't need to proceed more than log m times, because after that the graph becomes empty. Let's see this in picture. I start with this should be C2. But anyway, yeah. I start with the graph, then compute expanded decomposition. The cut is of size m over 2, right? And then next, I take, I start, this is the red edges here. Take the graph that is induced by the red edges here. This is the graph induced by the red edges. Okay. This graph has at most m over 2 edges. And then compute an expanded decomposition of this graph. And then this is a graph induced by the intercluster edges of this. So then you go to the next one. This graph is half again. And you can proceed log m times. Yeah.
Also, when you say induced, does it mean it only has the edges that we selected and then no other edges?
Yeah. It means this exactly. Just mean, yeah. G1 is induced by a set of edges, so it just means it's just a graph that has this exactly set of edges. Question about this picture, why how I define each of the GI and why there are at most log m iterations. Okay. So what do we have so far? Okay. We have that you start with the graph with m edges, then it kind of reduce by half, and this is of size something close to constant, basically. And we also know that each connected component here, there are expander, right? Every connected component is on expander, and all these graphs share the same set of nodes, right? It's just that, and this graph partition edge set of original graph. For every edge in original graph G, it will go to some of this graph. So we really just partition edge set of the graph into log m many graph, and for each of the graph here, it's just a collection of expanders. Okay. So what do we have from here? You can just say that here I just partition the edge set, right? So that each of the part in the let's say this is a partition, call it x1 up to xz, each part. This partition edge set, this is a partition. The edge set here is partitioned into many parts, and each part here, xi, is an expander. It's one over log expander. And we also know that each vertex will appear in at most log m expanders. Just because, yeah, there are log m many graphs here. So each node, if I fix one node V, one node A, it will be in some component. It will be in some component here, another and A will be in this component, A will be in this component. So every node is in at most log m expanders from all these parts. Yeah.
But each edge is only one of them, right?
Each edge appears only in one, but each node appears in log m many. Okay. Are we good? So this is kind of another way to view any graph again. Like from expanded decomposition, we know before that given any graph, you can remove 5 fractions and you get a bunch of five expanders. And here it says that, okay, given any graph, you can partition edges into parts so that each part induces a good expander, like 1 over log expander. And it's like a kind of log n layer of graph here. Okay. So let's see the application now. So we will use this repeated expanded decomposition to build something called edge sparsifier or graph. So what is edge sparsifier? For cuts. So you have a graph. Then now I want to build another weighted graph which share the same set of nodes, but the edge set are different. In this case, the edge set here is actually going to be a subset of E. E prime is going to be subset of E. But now this guy has weight. And what I want is that this graph H, who has only like O tilde n weighted edges. What is O tilde? It means I don't care about polylog factors. Means like n polylog n. So this graph is sparse. It's not dense because dense graph can have n square edges. This is sparse. But at the same time, like the cut size on every cut, for every cut, the cut size here is basically the same. The cut size in G is basically the same in H, up to like 1 plus epsilon factor. So I hope you understand this. Any question about this object, the definition?
Is the original graph weighted as well, or?
You can think of the original graph as weighted too. Yeah. But for now, maybe just for this slide, think of it as unweighted. Yeah. So this really is just the number of edges. But the algorithm that I'm gonna present will generalize to weighted case.
Okay.
Yeah.
So assuming point 1 is true, point 2 is true, right?
The point 1, this one doesn't say anything about this one. No, because I could just, if I just want point 1, I could just return empty graph. It has no edges, but it doesn't preserve anything about G. So the point here is like, I have a graph G that could be dense. I can compress it to something small, yet it preserves all cut size. Can anyone tell me like why would this thing could be useful? Can you think of some application? Yeah.
Like regimes with limited memory, we want to try and preserve the structure of cuts for whatever reason.
Yeah, like imagine you have some really dense graph, and now you just want to compress it. Like you have limited memories. If the graph is like 1 billion nodes and it's dense, then it's like I don't know, you cannot store it. But if you sparsify it to like order of 1 billion nodes, then you can now store it. Also, if you have any graph that's dense, maybe you sparsify it. It now has basically the same cut information. Now you maybe just want to compute minimum cut in this specified graph. Now the algorithm is faster.
Also, like in general, would it be possible to make a graph that, like, every cut encodes some information, or like kind of maybe so it's useful to retrieve some data from that?
It could be, yeah. So right now, like what we preserve here is just like some number for every cut. It preserves the value. I'm not sure how to encode it, but yeah, I'm not sure. Yeah. Okay. More questions? All right. So let me tell you how to solve this. We're gonna show how to do this, right? And the pattern is the same. Let's solve it on expander, then do it on general graph. So on expander, it's gonna be simple. There is a linear time algorithm for it. And the algorithm is just this. Look at each edge UV. Then you're gonna you sample this edge. You put this edge into your graph H with probability PE. And what's PE? It's just something that looks like 1 over min of degree U and degree V. Okay? If you ignore like all the constants and something here, something like 1 here. Like I need to put 1 here just so that like the probability is not more than 1. Otherwise, it doesn't make sense. This is just like something that you can compute in constant time again. Just look at you have your node U and V. You have an edge UV. Look at the mean degree between U and V, and then sample with rate. Something like if U has degree less than V, then sample with rate 1 over degree of U. That's it. And if you sample with this probability, and if you did sample it, then put it with this weight. And this makes sense because like at least we want the expected weight to be 1. Right? You sample with PE probability, and then if you sample, then the weight that you should put is 1 over PE, so that the expected weight is like just multiply to 1, so that this is like a not biased. Okay. It shouldn't be clear to you why this works, and I will need to skip actually why it works, but the proof is not too crazy and you can have a look. But actually, there is a more general proof which says this. So as long as you sample each edge with probability that exceed this threshold, then people show that this will give you 1 plus epsilon approximation. What is this threshold? It's just basically the same thing here, but like the phi mean degree there is just the value of mean cut between U and V. Now, but we know that we know before from some slides ago that phi UV on expander is just like lambda UV, the mean cut from U to V. This is easy to compute, at least easy to lower bound on expander. Right? This is just at least like 5 times mean degree. Okay. So I can just like define PE to be like replace this thing with this thing. If that's the case, then P of UV is at least this threshold. Because I put something, like I replace this with something smaller. So that only get higher. So the probability that I sample is kind of more than my threshold, more than the required threshold. Okay, so I will not prove this, okay, but it works. But now let's try to analyze the size. We can say that actually the size of H now should be something small. Okay. So let's see why. Okay. So yeah, maybe I do it on the board. Okay. So, okay. Maybe it might be constructive to understand some example. Suppose that the graph actually, let's say that G is a clique. Okay. If G is a clique, then what would this algorithm do? Well, like for every edge here, U and V, right? The degree of every node is just n minus 1. So it means that for all nodes, if G is a clique, then it means that in this case, you really just sample each edge with probability something like log n over n. Like, so we sample UV with something like yeah, some constant in log n. I don't care about this that much. It's just this thing times log n over n minus 1. So in the clique, we really just gonna sample every edge with this probability. And so it will become like a graph, basically a random graph where each edge appear with this probability. And it's gonna be sparse because yeah, there are like the number of edges is gonna be in expectation is something like n choose 2 times this thing call it P, and that's something like n log n order. Okay. Right. So what if the graph is a star? In this case, what's the probability that we will pick this edge? One. Right. I mean, the degree here is n, the degree here is 1. So we kind of need to sample that, like our sample probability depends on the lower degree guy. So we're gonna pick every edge. Like we don't do anything. So the point of this is that like whether we're gonna pick an edge or not, you kind of look at the lower degree endpoint of it, and then analyze it. So let's try to think like this. Now let's look at any graph. Look at any graph. Look at any edge. Okay, SUV. And then let's say that I'm gonna assign the direction to each edge. I assign to this if degree of u is less than degree of v. Okay. And then and now we're gonna get some kind of directed graph. Maybe like some, yeah, just some direction. Okay. Okay. So assign each edge to its lower degree endpoint. Okay. And now let's look at this graph and maybe look at some node V. Look at all the edge assigned to it. Okay. For example, in this graph, everyone kind of assigned to like this. So this node has no assignment. This node has one edge assigned to it. Okay. So for every node, now let's look at general case. For every node, look at all edges assigned to it. How many edges can assign to it? Well, the number of edges, yeah. The number of edges assigned to some node is at most degree of that node, obviously. Right. Okay. And for and let's maybe call this u, so that is agreed. Yeah. So the number of edges assigned to any node u, this thing is at most degree of u. Okay. Now for the guy that is assigned to u, what is the sample probability of these edges? Something like 1 over degree of u, right? Because it assigned to u, so u is a lower degree endpoint. So we sample this with prop something like 1 over degree of u, some log factor, some constant, 100 phi or something, yeah, doesn't matter. But it's something like 1 over degree of u. There are degree of u edges assigned to it. We sample it with something like 1 over degree of u. So we basically, it means what? It means that so each vertex will basically sample something like log n edges that is assigned to it. Okay. So each node will kind of responsible for like log n edges. So that's why we get this bound. So this is a kind of in expectation, but you can show concentration and give high probability bound easily. Question about this? Okay. So now we see like how to do it on an expander. It's just quite easy. Okay. Linear time algorithm would work. Let's try to do this in general graph. Okay. Well, we know how to do things on expander. So what we're gonna do is I'm gonna just compute the repeated expanded decomposition of the graph. And it kind of partition edge set to many expander. Now, for each expander, we know how to specify it, so do that. The degree sampling algorithm that we just see, apply it to this expander, and let's call the specified expander xi theta. given xi, which is the expander, sparsify it and call it xi tilde. And then union all this specified expander, and that's it. Union all this thing and return it as your graph, as your specifier. Okay. 1 sec. Okay. So with picture, like you have a graph here. Okay. You do expanded, like repeated expanded decomposition to get this picture. Now for each of the expander here, this could be dense, right? We just know that it has good expansion. It could be dense. This is a xi. Then just specify xi here to be xi tilde. Specify each of these guys. Specify them. Specify this, and then you get xi tilde. And then just union all the xi tilde. Is the algorithm clear? Okay. All right. So let's analyze the size. Okay. Well, what's the size? The size of hash. The size of hash is just basically the sum over all xi, right? The number of edges in xi tilde. Okay. But this thing is specified, so it's basically the number of nodes. Like something like this, the number of nodes in xi tilde. Make sense? This is like a specified graph. So the number of edges is close to the number of nodes. Okay. And now you count what's the total number of nodes on all the xi. And xi and xi tilde have the same set of nodes, so this is just okay. So what should this be? Well, like there are like you can say that this is like a sum over all, like you kind of sum over the number of nodes here. Okay? And you kind of group it into groups here, like the blue one, the red one, the green one, and so on. But the blue one has size n, red one has size n, green one has size the total number of nodes is n. In every group here, the number of nodes is n. So like maybe let me be precise. This is something like log n over this thing, right? Okay. Okay. But phi here is like 1 over log. So this is like log square. Okay. So now this is like it's gonna be, I claim it's gonna be log n times log square over this thing. Because this thing is n log n. Question about this? Yeah.
Why is that thing n log n?
Yeah, because if you look at you count the total number of nodes in our xi. Now each node, actually log m, each node appears in at most log m many expanders.
Oh, it makes sense because we have like log m kind of steps, right?
Yeah, yeah. Each node appears in log m many expanders. So this is kind of, you count each node this many times. So that's it. Yeah. That's why you get this size. Okay. Now why like the approximation is correct? Like I claim that h is still like a 1 plus epsilon approximation, like 1 plus epsilon cut sparsifier, like it preserves each cut within 1 plus epsilon factor. Right, and the reason is just that exercise. But the idea is just this. If I say in one sentence, like union of sparsifier is a sparsifier of the union, but if I say it quickly, it doesn't mean anything. So let's look at this. This is like true in general. If you have a graph, and I partition a set of this graph into 2 parts, let's call it G1 and G2. And then look at these two edge set. Then I kind of specify each of them separately. I specify G1 to like let G1 theta and G2 theta to be alpha specifier of G1 and G2 respectively. Right? And now, if I union this specifier together and call this thing G theta, then the claim is that G theta is a alpha specifier of G. Okay. Before I prove, is the claim clear? Is this clear? Okay, so let me prove it. Well, the idea is just that if you have G and you look at any cut as V minus S, ST, maybe ST, then well, like the cut size in G, like, and let's say I partition it into G1 and G2, right? Then this cut size is just exactly ST, maybe, yeah, let's call this thing, plus Y, well, like each edge is partitioned into one of G1 or G2, so each edge that cross the cut must appear in one of these. And then now I have that G1 theta is a specifier of G1, and G2 theta is a specifier of G2. So if these things are basically close to each other, then when I multiply this, I add this together, it's just gonna be close to this thing. Okay. So it means like G theta is just a union of G1 theta and G2 theta. So this is true. But if both of these is like close to each other, then this must be close to each other too. So in this case, it's just like a kind of partition into 2 parts, specify each part, and union them. It works. But here we just partition it into many parts. Just apply the same argument many times. Okay. So I hope you are convinced that we can, yeah.
When did we ever prove like the 1 plus epsilon approximation?
Say again?
Like, did we ever prove the 1 plus epsilon?
No, like this is a thing that I skip.
Oh.
Like, like on expanders. Yeah. I just claim this thing.
Oh.
Yeah.
So if you're scribing, is this like some proof that we?
You don't need to scribe. You can just refer to this thing.
Okay.
Yeah. The proof is not too crazy, and if you want, you can look it up. Yeah. It's like nice proof, but assuming that this algorithm on expander works, gives you 1 plus epsilon approximation, then the reason that the algorithm on general graph gives you 1 plus epsilon approximation, just follow from here, proof here. Okay, so we know now how to get a sparsifier, a cut sparsifier. So let me summarize. So what have we learned so far? Well, one point that you should get is like, okay, algorithm on expander usually becomes simplified. Whatever problem you want, as long as it's kind of about cuts, flow, connectivity, usually it's just easy. Okay. And but not all graphs are expander, so we use expanded decomposition to decompose it into expanders. Moreover, if you repeatedly applying it to the cut, okay, then you get repeated expanded decomposition, and you just saw how to use it to do a sparsifier for cuts. So this is a picture for expanded decomposition, and this is repeated expanded decomposition. So tomorrow on exercise session, I will consider 2 things. It's gonna be extension of expanded decomposition in 2 ways. One is called dynamic expanded decomposition. Another is called boundary linked expanded decomposition. And we will I will kind of let you try to I kind of gonna state it and let you try to prove it. It's gonna be a kind of good exercise that you understand things in class. Yeah. So see you tomorrow. Yeah.